It's you there. Let's get the recording going here. So we got up to the Mandelstam variables. I don't remember if I pointed out that there can be some ambiguity in the naming of the Mandelstam variables. So if you, let's see, if you have something like, well, take Compton scattering, where you've got a diagram like this and a diagram like this one here. Let me draw it again. So it's the time-like and a space-like channel. So you have the particles coming like this. Wait, no, this is not Compton scattering. What do I want here? So if we have an electron and a photon coming in, then an electron, and we could draw it this way. But then when we draw this one, okay, so we've got the electron and photon coming in, and now it's natural enough to draw it that way, except now the problem is, this is K1 and K2, this is K1 and K2. The Mandelstam picture just puts a blob here and has something like 2 in and 2 out. So T is this one minus that one squared. Whoops. P1 minus K1, K2 squared. And then if this is P2, I'm not sure how to label these, K1. Where you put these determines, which one is T and which one is U. That's the issue, and this is going to come out wrong because here you would be calling this P2 P1, so that T would be the magnitude squared of P1 minus P2, whereas here T would be P1 minus K2. So what you want to do is flip these, make these the same, so that you have K2 coming out here, and then these two end up both being P1 minus K2. Now, I worked all through this, and then I looked up what someone else. Hey, Alex, hello. I looked up what someone else had done online and posted, and they had the opposite assignment for T and U. So it's important when you lay out your calculation to specify, make sure your different diagrams are consistent, and you specify what S, T, and U are, or whatever variables you end up using. There could be more if there are more particles involved. All right, that said, I think the next thing to do, at least in terms of the notes, is to work through an example. I think you've just did the Compton calculation yourselves, and I think everyone got the matrix elements right. So I'm not sure how much of that we need to do. I could run through the Compton or the Baba scattering. What I've done, and let's see, let me see where it is. Yeah, those two examples are the rest of. No, this is This is weird. I thought I'd taken this out. Well, oh, no, I'm sorry. The ultra-relativistic Compton is the last thing in chapter 10. And what I asked you to do last time was to go through your solution from the end of last semester and compare to my solution and see where there were any differences, if you find any mistakes in mine, or if it helps you spot any mistakes in yours. So where are you in terms of the assignments? There were 3 things I think I suggested you do. One was to compare your final exam to my solution for the Compton at the end of chapter 10. Did anybody have any questions doing that? Okay, I tried to make it a fairly concise calculation while including enough detail, but using as many tricks as I could think of to make it shorter. So, you know, check and see. You may pick up a trick or two for making them shorter. If you don't have any questions on that, then we should move right on to chapter 11. Now, in chapter 11, I develop the idea of the decay rate and the cross section, which I think will take us a little while to discuss today. And then, let's see, I started on a Baba example. I don't know that I finished that, but in section 11.5, I lay out details of the Compton problem, where I'm asking you to compute the Klein-Nishina cross section. Now, the Klein-Nishina, this will be like the exam you did, but not the ultra-relativistic case. This will include the masses. And there are a lot of steps to this. You know how to find matrix elements. It shouldn't be terribly hard, although it can take you a while to carefully work through the squared matrix elements, put those together. But then that's only part of the problem of finding the differential cross-section. To find the differential cross-section, I'll develop the formula for that today. It's proportional to that squared matrix element, but there are some other factors that come in. There's a flux element that needs to be included, and various factors of the energy and so on that need to be included in calculating a differential cross-section. Then you have to do something like, let's see, 4n minus 1 integrations, some of which are non-trivial. You have a lot of Dirac delta functions, but you have to change variables enough that you can actually do them in some coordinates, in some frame of reference. I want you to work in the frame of reference in which the initial electron is at rest. And I write out the four momenta, and basically you have to put these integrals in terms of those. Now, conservation of momentum will let you integrate over all the final electron momenta immediately. That leaves you integrations over the final photon momentum. You have a delta function on the energy, so the time component is immediate. And then the spatial component for the photon, if you write it in spherical coordinates, then that introduces the angles you're going to want in some experiment, and you can integrate over the magnitude. The magnitude of the 3-vector part is equal to the energy because it's a null vector. So you can actually do that last integral, and it leaves you with 2 angular integrals. Rather than doing those integrals, you write the differential cross-section. So if you do those, you have the total cross-section, the total probability of scattering. If you leave those, it's the differential cross-section. and you can find the probability for scattering through various theta and phi. So I want you to work through that process. I spent the week doing it. I've done it. I don't know how far you've gotten with it. Have any of you gotten it yet? The Klein-Nishina formula? Okay, I know I assigned it, so you're negligent, so there. But so try it, okay? And email me or Zoom with me if you have questions on it. I think you know how to find the matrix elements. That's only half the problem. In section, the new section, I just posted this in section 11.5, I lay out some benchmarks along the way so you can check your work. I give you the squared matrix element for the S channel, so you can check that. The T channel is very similar. The interference term is not all that bad, so you'll be able to get the squared matrix element. You can easily check by setting the mass to 0 that it agrees with our results for the ultra relativistic case. Okay, then you need to go through these several integrals to find the final formula. And you need to express that matrix element, which will be written in terms of Mandelstam variables and some sort of long, complicated looking thing. Took about 3 lines in LaTeX. Write that in terms of the laboratory frame momenta explicitly. And after you've done all these integrals, that'll end up being an expression just in terms of the energy of the initial photon and the angle of the scatter. It helps to write it in terms of the energy of the final photon as well, where that's already given by conservation of energy. So read through 11.5 and follow the steps. Now, going back though to the beginning of 11.5, there are some complications that arise when we try to compute a cross section. One thing that goes into the calculation is the square of the matrix, and that's the square. Let me write this out. Oh, geez. Tripping over stuff here. Okay, so the scattering matrix is basically an identity minus I times T. And then we wrote T as possibly 2 pi, and I think we used 2 pi to the 4th. And the conservation of momentum here. So the total momentum conservation times the matrix elements initial to final state. And then we've spent some time calculating this. Now, what we're actually going to need is the square of the full matrix element, which is going to be 2 pi to the 8th times del 4 of the sum of the momenta times another del 4 of the sum of the momenta, and that matrix element squared. Well, we've got this and we know what 2 pi is. What we don't know how to handle yet is the square of a delta function, or the square of 4 delta functions. This sets the sum of the p's to 0, so if I do that, this is a delta function evaluated at 0, which is quite infinite. And we need a way to handle that. What's normally used is it's called a box normalization. If we restrict our attention to a finite box, so say a cube of length L and duration capital T, then the momenta within that box become discrete. The integrals turn to a sum, and we can actually come up with an expression for that sum over the volume of the box, and it ends up being proportional to the volume of the box. Now, the volume of the box is going to go to infinity eventually, but what happens in the calculation of the cross-section is that you get additional factors depending on that volume, and they cancel. So in the end, that volume drops out, and we can go ahead and take the limit as the volume of the box goes to infinity, and it doesn't make our cross-section diverge. Now, to see how this works, we can do just a classical system. Let me suppose we have a plane wave. Suppose psi is some e to the I k dot x, just a simple plane wave. Then the normalization of this psi is going to be c squared integral of e to the I k dot x minus e to the I k dot x over all space, and this diverges because that's just one, and we're integrating over all space. Now, if we restrict to a box, then this just becomes the volume of the box times c squared. And we can normalize within the box, let psi be 1 over the square root of the volume of the box, e to the I k dot x. And now within the box, that is fully normalized. The other thing that happens is that these wave numbers or momenta become discrete, and then we can look at Pn with Pm, and that's going to be a Kronecker Nm. Whereas if we had continuous P with Q, this would be a delta. This would be a direct delta. So we get away from the divergence of the Dirac delta by going to this discrete thing. And then if these happen to be equal, all right, so if we were looking at P with P here, that would be delta of 0. But if we look at Pn with Pn, if we look at the discrete case, Pn with Pn, that's delta Nn, which is just 1. And so we end up with something finite when we normalize this in the box. So now we have to do this all relativistically. Let me see. The first thing we have to deal with relativistically is the normalization of a relativistic momentum state. Let's see. Where do we, yeah, okay. So let's consider how volumes change.
So essentially you're adding a weighting factor to our original wave function, but this weighting factor can diverge.
The weighting factor, which the V,
the V. Yeah, the V. Yeah. Well, yeah. The V.
Yeah, we could let the box be as large as we like. That means we can take the momenta to be as close as we like, and we could even approximate the discrete case by an integral. We can, the box can be huge. Doesn't matter how big V is here. these are all still finite. So, so even in the box normalization, writing things as integrals is permissible. It's a good approximation that becomes exact in the limit as the box goes to infinity. Let's see, have I answered your question? I'm not exactly sure. You're good? Okay.
So I just want to be clear also. So we've just taken a really long time to say that we're restricting our attention to a specific volume.
Yeah, right. Yeah, yeah.
All right.
Let it be a cubic box, just so every side is L. The time dimension will be some capital T. Now,
And we just normalize it to that box, like that box is the universe.
yeah, that's right. That's right. And now what happens to the volume of the box relativistically is you get Lorenz contraction in one direction. So you get a 1 minus beta squared factor. Whichever direction you are moving the box, you'll get that factor of contraction. Now, energies are the fourth component of a 4-vector, and they change with a factor of gamma, which is 1 over this factor. And so the product E prime V prime, often there's a 2 here, is Lorenz invariant. So if we put an E with each V, now we're talking about something that's Lorenz invariant.
What would you call that? EV.
Ev.
Does that have a connection to the cosmological constant?
EV.
Sometimes V sounds like energy volume.
Energy volume. What are the units of the cosmological constant? Let's see. It should be 1 over length squared. So let's see. That's a length squared. So 1 over something like that could be the cosmological constant. I mean, we're just in some box somewhere, right? And we're just normalizing some wave function. So there's not a direct relationship here to the cosmological constant, although it could emerge as something of this sort. The reason for a factor of 2 here, when you're integrating a delta function over space-time, if you have something like d4x or d4p, sorry, delta. Yeah, suppose you have a delta function in the energy, the norm of some 4-vector like this. You can write this as 1 over 2e times a delta in e minus the square root of p squared plus n squared. Actually, a sum of 2 such things. This would be, say, the positive energy contribution, and then you'd have a negative energy contribution minus e here.
We already seen this with the anti-particle particle case, right? Or distinction.
Yeah, this would be an antiparticle. All I'm actually doing is rewriting this delta function using the usual relationship for delta of a function of x is the sum over the zeros, 1 over magnitude f prime at the ith 0 times delta of x minus xi. Have you all had a chance to prove that identity for delta functions? I think I've asked you to do that, and other people have probably asked you to do it too. So if you haven't done it, go do it. So I'm just using that, right? This has got an e squared in it. 2e is the derivative of e squared. So that's all I'm doing. And then there are 2 cases there are 2 roots for positive and negative, and then the same kind of factor here with a plus sign. And because we're dealing with a well-defined scattering problem, we're dealing with positive energy, say electrons and photons in the case of Compton scattering. So we don't need to worry with the negative solution. We can look at exactly this, but that's the reason that you may see a 2e here instead of an e. Getting the factors of 2 and pi right turns out to be hard. I've actually worked out the Klein-Nishina formula so I can help you guys with it. Only my answer is off by about, what was it, maybe 4. I've got an extra 4 pi. I'm not sure where it comes from. Don't be alarmed if you're off by some factors of 2 or pi or something. There are different ways to normalize these cross-section calculations, and it takes some extra care to get those normalizations just right. I'm still looking for my factor of 4 pi. I found a few potential factors of 2, but okay. So what happens is the box normalization is we can use this factor. We can use the EV factor as a relativistic normalization. A Lorenz invariant normalization. So the inner product of 2 momentum states in our finite box is going to be some normalization constant, and then we're going to have a 2EV here. Did I put the 2? I did put the 2 delta PP. And we want that to just be delta P prime. So we choose A to be 2EV. If I've got that, yeah. So the normalized momentum state is root 2EV times, this is normalized, times the unnormalized momentum state. So we'll be introducing some additional factors of root 2EV when we define our matrix elements. Remember, our matrix elements are comprised of the inner product of momentum states. And so for each of those incoming and outgoing momenta, we're going to need a square root of 2EV in the appropriate place. So we have a relativistic matrix element that's the product over initial momenta with a 2EV to the 1/2. Do I have this the right way? Yeah. And then a product over the final. And let's call that 2EJV to the 1/2. And then we have the matrix element in terms of the unnormalized momenta there. So we'll be inserting these factors, and you see these bring in some factors of the volume as well. And this is how it happens that when we compute decay rates or differential cross sections, the volumes end up canceling out. So let's first look at the easier case, a decay rate. It's easier only because there's only one particle in the initial state. Otherwise, it's pretty much the same as a scattering problem, where you have maybe 2 particles in and 2 particles out, or 2 in and several out. A decay can lead from 1 particle to any number of product particles as well. So the matrix element we want to compute, let's see, I think I wrote this. We have IT squared we're going to need, and that's going to have a 2 pi to the 8th and a del 4 of the sum of the momenta. And then we can write the second delta as del 4 of 0. And then the matrix element. M squared. And by making it discrete, we can resolve the problem of that delta function. So now we have D3 of the del 3 of P minus P prime, right? That's normalized to 1. The sum, when we take D3P to be a sum, then it's going to need this normalization, 2 pi h bar over L. So let me write this and I'll tell you why. We need 2 pi h bar over L cubed times the sum on n. That's because the momenta are going to be of this order, right? They're restricted to multiples of this, 2 pi n h bar over L. And basically, the 2 pi h bar is the size of an area element in phase space. But in a box of length L, the momenta are multiples of that. That's like the wavelength, the de Broglie wavelength. So multiples of that wavelength. So for this reason, a momentum integral ends up being a sum times this factor. And when we want to normalize the delta function, right? This full expression, this expression up here. Let me work up here. All right, this one is going to be, well, we have this factor by h bar over L cubed. Then we have a sum on n. And we know that the delta is going to be proportional to a Kronecker. So we get some lambda delta nn prime now, where this goes to Pn minus Pn prime in the discrete case. So we need lambda to know how the delta function turns into P minus P prime is going to be replaced by lambda's got to be 1 over this factor times the Kronecker. So this is going to be L over 2 pi h bar cubed delta nn prime. So we're going to make that replacement for the delta function. Then we can actually write this as P prime, where we keep in mind that these are discrete, but we're letting the box be large. Okay, so 2 pi cubed delta L 3 minus Q, say, is going to be replaced by L cubed is just the volume, and h bar is 1. So delta P cubed. And then when we set this argument to 0, we have 2 pi cubed delta 3 of 0 is going to be replaced just by V delta 0, 0, which is just V. And we're free to put in factors of Planck's constant and the speed of light anytime we need them. So let's see, can we see this okay? Try a different marker here. The 4-dimensional case is just the same. We have one more dimension to our cube and its extent is capital T. So we have 2 pi to the 4th, del 4 at 0 is going to go to V times the time extent of the box in our integral up here. So this is just going to get replaced by VT for our box normalization. Okay, so far so good. Now, what happens to IT squared? Okay, to erase some here. So now we've used 2 pi down here. So we're left with 2 pi to the 4th, del 4 on the sum of the momenta. And then here we get a V and a T. And now we also get factors, since we have m squared, okay? We have this m squared, but I'm going to write that in terms of the relativistically normalized matrix element. Let me call it curly m here, the relativistic one. And now we get these factors of 1 over twice the energy times the volume. Since there's only one incoming particle, I can just write 2e for the initial particle times the volume. And then we have a product of all of the outgoing particles. Say we have n outgoing particles. And for each of those, we have 2ev. And there's no square root because we've squared the matrix element. So we have a product of all of these inverse. Let me see, am I right here? Have I got, yeah, I've got everything. Okay, so now, almost there for the decay rate. The decay rate is going to be given by integrating over the whole final phase space. So if we're summing up the total decay rate, we sum over all of the final configuration space, that is all positions and all momenta, normalized by the by 2 pi, by the volume element that h bar is 1 cubed. So there's a 2 pi cubed here times the matrix element squared. So now we have to integrate this expression over those variables, and we're gonna write that integral. So, let's see what happens. We've got a 1 over 2 ev. We've got a product of 2 eiv inverse. Let's see, let's put our integral here, d3 pi over 2 pi cubed. I'm setting h bar to 1 here. Then the integral over the x's. And 2 pi to the 4th, del 4, sum of the momenta, and the matrix element squared. Did I get that? There's a VT somewhere. I lost the VT. So put in a VT and we've got the matrix element squared. Okay. So now what happens is, remember this matrix element only depends on the momenta. We've written it in momentum space. So the spatial integral just gives the volume, and that's going to be a volume to the nth power. This product includes 1 over the volume to the nth power. So that is going to cancel the x integral. Then this v cancels with the vt. And so the rate is then just this, this total probability for decay per unit time. All I have to do is divide by the time, and we get the total rate gamma is equal to, oh gosh, what do we have here? 2 pi to the 4th, 1 over twice the energy of the initial particle, which if you work in the rest frame of the decaying particle, it's just the mass of that decaying particle. Then we have del 4 conservation of momentum, and the integral over all d3 pi over twice ei. This is a relativistic volume element. I'll say why in just a second. I've divided by the time, and then we have the matrix element. Everything here is relativistically invariant, except this energy right here. d3p over 2e. d3p is a volume in momentum space, which is an inverse volume in position space. Momenta and energies go as 1 over length. If you use h bar and c judiciously, a momentum, a mass, or an energy, they're all inverse lengths. So d3p is an inverse volume. So this is 1 over ev dimensionally. So this is a Lorenz invariant volume element. The matrix element is now Lorenz invariant. The delta function over conservation of momentum, invariant. The only thing that depends on the frame of reference is this energy. And this is exactly what it takes to bring in the time dilation in your rate. Okay, the rate is the number of decays per unit time. And so you need that time dilation factor, and it exactly comes from that energy. So this all works out as a relativistic rate of decay of a particle of energy EP into n particles of various energies. Now, if you want a differential rate, if you want to know, what is the rate of decay into like a pion, then you can leave the pion variable as d3p, not integrate over it, and find out how d gamma depends on the infinitesimal volume element in momentum space for your final pions. So changing the direction or the total momentum of your final pion can lead to different decay rates just by the coefficient of the d3p there. So that's decay rate. Now, for cross section, and notice, I promised you lots of integrals, right? So, we are going to integrate here over basically all the final states. And so to calculate a cross section, we need to carry out those integrals, and we're doing lots of integrals over delta functions, and it's a little messy, right? It's like any messy calculation. It gets neater and neater the more times you do it, and you get closer and closer to doing it right. So, cross sections. We're gonna want this relationship for the integrated matrix element, but I probably don't have room to leave it on the board. We've got to go through a little bit of stuff beforehand, but I will pull that in eventually. The place we want to start is a convenient frame of reference, which often turns out to be the rest frame of the target particle. Now, in a collider, it's the center of mass frame, right? you can work these things out in any frame of reference, but we have to come up with a relativistically invariant way of expressing the cross-section. We'll start with a non-relativistic version. Suppose we have a beam of density at rho 1 and target of number density of particles rho 2. And a non-degenerate marker. Then what we can say, there's an incoming flux, the incident flux is going to be rho 1 times the velocity of the incoming beam. Remember that we're in the rest frame of the target particle. So the only relative velocity is that velocity of the incoming beam. So now the number of decays per unit volume per unit time is going to be proportional to the product of these. It's going to be proportional to the product of the target density times the incoming flux. And this is a number per unit volume per unit time. Okay, these are each number per unit volume. So we've got volume squared. So let's see, dimensionally, we've got length over time. We've got length cubed twice. And that's got to be a number per unit volume per unit time. So the times check, one set of volumes goes out, and L over L cubed gives us 1 over L squared. So this coefficient is going to have units of area. The units of area we use are called barns. You familiar with barns? As in, you can't hit the broad side of a, you know, this is really what people talk about, these particle collisions in, you know, hitting like a quark on a quark in a collider. I think you often have cross sections of millibarns. A barn is about, I think it's like 10 to the minus 24th square meters. It's a really small area, sort of comparable, somewhere between the size of an atom and the size of a nucleus. But, you know, for a rare event, you might be looking at a probability proportional to something like picobarns, you know, very small units of probability. You can think of this cross section. This is the total cross section for this interaction, and it's you can think of it as a cross sectional area of the target. How likely are you to, you know, hit the target? Well, it's proportional to an area, and you know, it's not exactly an area, but it's an effective area. So let me think. There's an equality you can draw here. If yeah, so the probability of, say, electrons scattering off of a nucleus, or an alpha particle scattering off of a nucleus, the probability of some scatter rather than just passing past can be equated to the probability of hitting a disk of a certain size. What's the probability that you hit that disk? How big does that disk have to be so that the probability of hitting it with your incident beam is the same as the total probability of some kind of scatter off your actual nucleus? And so in that sense, we're coming up with an area for the total cross section. Now, we're interested in more than the total cross section. We're ultimately interested in the differential cross section. So what is the probability for scattering through this or that angle? And we'll get there. First, we write an expression for the total cross section, and then we can, from the expression we get, it's easy to see how to make it differential. So now, this tells us the cross section, right? So the cross section is just the number of scatters per unit volume, per unit time, divided by the number of target particles, number density of target particles times the incident flux of particles. And now we have written this in the rest frame of the target particle. What we want to do is make this expression relativistic. And the actually, most of it just falls out. You know, if we get an energy times the volume, we know that's Lorenz invariant already, and we will eventually. But it's the relative velocity here that is manifestly not manifestly invariant, and we want to make it so. So let's see what we've got. We know what invariance we have because we have the momentum of particle 1 and the momentum of particle 2. And that's really what we have to work with here. So we have 3 Lorenz invariant quantities, P1 squared, P2 squared, and P1 dot P2. Each of those is manifestly Lorenz invariant. Now, let's write each of those in the rest frame of the particle. Well, we know that P1 squared is m squared c to the 4th. We know P2 squared is m2 squared m1 squared c to the 4th. Well, c squared. Let's keep them with units of momentum rather than energy. So c squared here, and then P1 dot P2. Remembering that we're in the rest frame of P2, so P2 can be written as M2, 1, 0. So the dot product only picks out the time part. Well, that means that we get M2 times C, and then the time component of P1 is M1 times C times gamma. And this is just what we need because gamma is a function of the velocity only. And we can find the magnitude of the velocity just by working with this expression. So if we take P1 dot P2 squared, then it's going to have an M2C squared, M1C squared. So I can divide by these two, P1 squared, P2 squared. And what is that? That's going to be gamma squared, which is 1 over 1 minus b squared over c squared, where that b squared is the thing we're after. We want the magnitude of the velocity. So now we just have to solve this expression for the velocity.
So is that an erroneous square on M1, or is that because we're... Oh, okay. All right. Yeah, got it.
Yeah, we needed another there. Let's see. So yeah, I'm squaring this so we get these guys squared, and that's just what we need here.
All right.
Yeah, it's momentum squared. Right. Think of each component of the force and momentum. Okay, so now we just solve. So let's see. 1 minus v squared over c squared is let's see. P1 squared, P2 squared over P1 dot P2 squared. And so do some solving here and bring the 1 to the other side. So V over C, and this is the magnitude of V now, is going to be the square root of 1 minus P1 squared, P2 squared over P1 dot P2 squared. And it's kind of convenient to notice that this product P1 dot P2 is just E1, E2, where up to factors of the speed of light, called the speed of light 1. So now, let me see. let's see. Well, over c squared. I'll keep the c's for the moment. Okay, so if I multiply this side by E1, E2, and then we have the magnitude V that we're after. And then, let's see, that is equal to c squared, this c squared here, times p1 dot p2 times the square root. So I can write this as the square root of p1 dot p2 squared minus p1 squared p2 squared. There we go. So the right-hand side of this is manifestly Lorenz invariant. Have we lost Guillermo, or is he thinking deeply? Oh, okay, sorry. You looked like you dozed off there. Wouldn't blame you. It's a nice, lazy afternoon. Okay, so sorry. So we can write V as this invariant, and we define this invariant. Let's let C equal 1, and define this invariant to be I. Usually 4i is what arises in our final formula, but we're going to define this object to be I. I'll put this c squared here. So I is just that square root factor. Okay. Is everyone clear on what I mean when I say manifestly Lorenz invariant? Any question on that? Yeah? No?
Yeah, it's just an algebraic combination of invariants.
Everything is a proper Lorenz invariant thing, right? So an expression like this, where all of the contractions are done with the metric, is Lorenz invariant because any up indices transform with a factor of the Lorenz transformation lambda mu nu. Any down indices transform with the inverse to that matrix. And the fact that these are all contracted puts these together and gives you 1. So any expression that's written in terms of 4 vectors or Lorenz tensors in which all indices are properly contracted, the only contractions are one up and one down index with no free indices, that is a Lorenz scalar. Under a Lorenz transformation, that will always remain the same. So the mass is Lorenz invariant. We know that, right? Masses don't change. This inner product between two, right? If this is P1 and P2, you don't exactly know what that is, but you do know that it doesn't change if you change your Lorenz frame of reference, right? Because these transform oppositely to that, and there's no leftover lambda. Okay, so everything in here is built out of these Lorenz invariant pieces. Therefore, I will not change if we go to boost to a different frame, say. It'll have exactly the same value. Okay, so now we want to incorporate that here, and I can write sigma as dn, and what do we want to do? If I put, let's see, so V is going to be I over E1, E2. So if I replace that, I'm going to have E1, E2 here, and dV, dt, rho 2, rho 1 times I here. So I get this expression where now this at least is Lorenz invariant, and we can then figure out what we do with the rest of these things.
Professor?
Yes, Alex.
Can I play voodoo scientist again really quick?
Go for it. What you got?
I just noticed on that invariant that you wrote down, if you divide both by c squared and identify the energy with the mass of each particle, then it looks like mass times mass So like this equation that you boxed,
This is
I'm looking at the left side.
Square. That's right.
I was looking at the left side.
Left side.
The left side. The left side. Yeah. So if you divide by c squared that invariant, it looks like if you equate the energies with the masses, it looks like mass times something, and that volume. If you take the c out, the time out.
This is the velocity.
Oh, pardon me.
Yeah. So this is these energies have gammas in them, right? So so this is gamma 1, gamma 2 times v. It's a complicated thing.
Never mind. Okay, sorry. Velocity makes more sense.
Okay. No, good to sort through what we have here. Yeah, it's not at all obvious that this thing should be Lorenz invariant, right? But we can write it this way, and that shows that it is, nonetheless, despite depending in fairly complicated ways on the velocity. Okay, so now let's see, how do we do this next? Yeah, we need, yeah, it helps to write it upside down. Let's write it upside down. Write it for dn again. Let's see, I was thinking these were in the numerator. So dn is our sigma times, let's see, what are we going to have? We've got some energies in the denominator. Yeah, so we have I, we have sigma, we have E1, we have E2. And now, what else? dV, dt. So we have our rho 2 dV. I'm going to write it. I'm going to put a volume down here and a rho 1 v up there. So that volume just cancels. And then we have a t dt here. Let's see, did I get everything? Rho 1, rho 2, I dv dt over E1, E2 times dn sigma. Okay, yeah, I think that's the same. Now, what I want to do, all right, rho 1 v1 is the number of incident particles. And now if I integrate over the volume, right, that's just some number now. If I integrate over this dV, this is just the number of particles of type 2. So these two just become the total numbers of particle 1 and particle 2. Then I integrate over time, and this becomes a total time t. So the number of interactions is now going to be written as n1, n2 times this invariant I times the cross section over v e1 e2 times t. And
I'm just a little bit hung up. So you labeled rho 1v as n1, but rho 2 dv is n2. So
all right, I'm going to integrate that, and I'm going to integrate that.
okay, all right. That's going to become an n. I got it.
Okay, so now the number per unit incident particle, per unit target particle, per unit time. Let's see. Yeah, if I think I want to divide by the time here, don't I? Yeah. Yeah, let's leave it this way. But and have I sigma t over v e1 e2. Okay, now this thing on the left though, this is really the probability of scattering. the number of scatters per unit incident and target particle is just the probability of scattering. And we've already computed that. That's this sum overall phase space, d3x, d3p, over 2 pi cubed, I think it was. Where did I put this? Yeah, there it is. So all of this is equal to this times our squared matrix element, I think. Yes, that's right, 2 pi cubed. This is equal to I sigma over times T over the E1, E2. And now we simply replace this by that expression that I apologize for having to erase earlier, that we derived for the rate. It's all this matrix element stuff, right? So this is going to be 2 pi to the 4th. Then, and I just have to copy this. 1 over 4 E1V E2V. Our delta function of momentum. Then the product of momentum integrals over the final energies, final momenta. Then we have this VT and the matrix element squared. So now you can see that the T is going to drop out. The VEE, okay, VE1, E2 here is going to cancel with Eve there. Then this remaining V is going to cancel with that, and the times cancel here. So skipping over the middle step, we have something that's actually fairly tame. What we have is, can you see where I'm writing it? Yeah, sigma is going to be 2 pi to the 4th, del 4, conservation of momentum. We're going to have 1 over 4i. That's called the flux factor. And then we have the sum over all, and we're integrating these guys somewhere. d3pi over 2ei times the matrix element squared as the cross section. Now, in practice, what we do is, well, if I don't do that integral, this is just some differential. That's the differential cross section. Now, but what happens in practice is that you, okay, suppose, as often happens, you have a 2 in and 2 out scatter. Then you're integrating over 2 of the particles coming out. Integrate over the momentum of one of those particles using the conservation of energy. So you've got 4 delta functions here. You can do 3 of those integrals immediately and be left with 1 energy integral. So now you have d sigma depending on the space-time, infinitesimal space-time volume of one of the final particles, say the photon scattering off the electron. And you can use one of the deltas to eliminate the time component, then express the rest, the spatial integral of the single final particle, say the final photon, as you write that in spherical coordinates in momentum space. So you're gonna have a d k naught, say for the photon electron scatter. You're gonna have a d k naught, but you're gonna have a delta of that residual from the conservation of momentum, and then you're gonna have a k, the magnitude of k squared d the magnitude of k times angular integrals. And this k for a photon is just the energy, right? Remember, a photon has 4 momentum. You basically have the energy or the frequency times 1 and some unit vector direction here. So the so this is E and En. So the magnitude in spherical coordinates here is just the energy. And so you can do that energy integral and you're left with just the angular integrals, which you do not do. So now you have the differential cross section d sigma d omega, and this is going to be dependent on d phi and sine theta d theta with stuff. So for a particle emerging at angle phi and angle theta, you have the expected part of the cross section without integrating it all up. So that's the differential cross section. And let's see. Oh, I still have problem 3 there, but let's see. So I started to try to do this for Baba scattering because in the previous example, I had computed the matrix element. And I haven't finished that up. Let's see, I have finished up the Compton case, and I do get the Klein-Nishina formula, which is very cool. I get the essential part of it. As I say, I'm off by 4 pi somewhere. But question is what to show you. Let's see. Yeah, going through any of these is going to be mucking about a bit. Let me show you one thing about the working this out in the Klein-Nishina case, because there's another way to write the total cross section, and I'm sure this is where I'm losing the 4 pi, because there are various ways you might write this, but we've gotten this formula, this formula for the differential cross section, and it's already in terms of a 3-dimensional integral. We can back off from this and write it as a full set of 4-dimensional integrals, and then track through as we integrate the energies and so on. It should give the same thing as substituting directly into this formula, but I haven't had time to establish that equivalence yet. I think when I do that, I'll probably find my 4 pi. But how are you guys holding up? Yeah, sort of. Okay, let me write down this formula, and then we'll see where we want to go from there. So what we can do is write the total cross section, and that's straightforward to do. And then to get the differential cross section, you just don't do some of the final integrals. So we can write the total cross section. I got some new markers here somewhere. Here, let's just. Let's see if this works. Actually, sometimes new ones don't, but oh, yes, good. Okay, so the total cross section, 1 over 2 pi squared, which isn't quite 4 pi because of the extra pi, but I'm not sure why that particular normalization came into this formula. But now we integrate over all of the final momenta. And here I'm thinking of the Klein-Nishina problem. So we're talking about an electron and a photon colliding and scattering as an electron and a photon. We're going to work in the frame where the electron is at rest. So we have full 4-dimensional integrals here, whereas in the formula below, I had already written those as 3 dimensions. Well, if this is multiplied by an energy delta function and you do the energy integral, you get that 1 over 2 times E. So these should be equivalent. And now what we've got, in order to solve the equations, we've got a p squared minus m squared. Only that introduces, what I'm trying to do here is fix the norm of this 4-vector p. And now when I write a p squared, I mean the 4-dimensional norm. If I mean the 3-dimensional norm, I'll put an arrow over the p. But one place where the normalization is funny is that delta function has units of 1 over the units of its argument. This is a delta function in energy squared or momentum squared. So it has units 1 over momentum squared, but we're really using it to fix the norm of the momentum. And as a scalar, as a single delta function, not a delta function p squared. So if I can put a normalization in there to correct the units, otherwise the units of sigma are not units of area, then I want to restrict to positive energies. So I put in step functions in the time components of these vectors. Let me write this as P2 naught. These are the final momenta of the photon and the electron. And then we have another delta function in the norm of k squared. So this is going to force k to be a null vector. And then the conservation of momentum for delta functions here, p1 plus k1 minus the outgoing momenta p2 minus k2. And then 1 over 4i times the matrix element squared. We can write I very easily in this case. Remember, I is the square root of P1. All right, these are the incoming particles. So P1 dot K1 squared minus P1 squared K1 squared. And this is just going to be the mass squared, but the norm of K is 0. So that second term drops out. And this is just the magnitude of P1 dot K1. And if we're in the frame of reference where the, well, it doesn't matter. We know that S, the Mandelstam variable, is P1 plus K1 squared. And if I square that out for the case of the electron and the photon, I get P1 squared is n squared. Then I get twice P1 dot K1. And then I get K1 squared, which is 0. So S minus m squared times a half is equal to P1 dot K1, and that's equal to I. So I can write this factor as 1 over twice S minus m squared in Mandelstand variables. We write our matrix element in terms of Mandelstam variables. And you can actually do the integrals in terms of Mandelstam variables as well. But it's not necessarily easier. You can do it either way. So that's the expression I used. And then I give you 3 or 4 benchmarks along the way to the Klein-Nishina So you can use that. Now, that's sort of all I've got today, because I spent the entire week doing this Compton problem and getting the Klein-Nishina to work out. It's maddening how tricky these things can be. But after doing squaring each matrix element several times and getting a slow consensus on the result, I just brute forced my way to figuring out what the full M squared turns into in the lab frame, and it actually came out to the right thing. I was a little surprised. So, it helps on these to work with somebody, right? Get in touch with one another, compare answers. I've tried to give you some benchmarks on this problem, but I want you guys to do some of these scattering problems. I will go on next time and I'll talk about maybe what happens with loops and virtual particles, and move on to some additional ideas. But I want you to keep computing things. Another problem that you can do is muon photoproduction, or muon production from an electron-positron collision. Let's see, which of those is most interesting? Yeah, probably an electron-positron collision that yields a muon anti-muon pair. That's another problem you can do. Right now, I think you've got plenty to think about with the Klein-Nishina formula. So, rather than trying to make up enough to say for another hour or so, go compute, right? Work this out and get in touch. We can Zoom, we can email, anytime, ask questions, work together, and, convince yourself that you're getting the right things step by step as I give them to you here. And I'll try to move on with stuff. Okay, so any questions? You're rested after the semester and you're eager to do a new QED problem, right? A couple of you look kind of tired. I get it. I totally hear you. But yeah, try these things and just be in touch if you have questions. Okay, now, while we're all here, is this time a good time for you? Monday afternoon, 2 o'clock? I know Alex has a difficulty with it next month. So we might want to shift the day, or we might want to make Alex watch the recordings. Yeah, let's cross that bridge when we come. We're almost there, aren't we? What is that? Another week or two, isn't it? Would another day be as good? Alex, is every day the same, or what's
it kind of changes. I think there's yeah, I don't really know. I don't know what some of the class schedule is a little different. So there's maybe some Fridays where I on paper have some free time, but it could be that there's just off paper stuff that's going on too. So I maybe, but I might be blocked the whole time, except for weekends. Presumably, but I don't know if people are.
Okay, well, yeah.
I can watch at night too.
You can Zoom with me on Saturdays or something and catch up.
Okay.
Let's, given that uncertainty, let's just keep it on Monday at 2. I've scheduled all of the Zooms now. Unless you would rather have more shorter meetings. I know, till the cows get home can be tiring. But
We might
sometimes
arrive
having,
at different times for each of us, for sure.
what's that? I'm sorry.
The cows might arrive at different
Oh,
times for different people.
Right. Yeah. And, we can take a break in the middle. That's fine too. I'm, anytime's going to work for me. I think I don't see that there's any strong preference for one day or one time over another. I think Friday might be a little awkward. That's one day I actually have some things scheduled, but other than that, we can be flexible, and I'm happy to Zoom with all of you any other time as well. So, if you get stuck on something, have questions, I want to keep moving with new material, but you've got plenty of exercises here. I have just posted a current version of the notes. I have written up the whole Klein-Nishina, but I've put enough that I think it'll step you through it without just telling you how to do it. Then the one other problem, I think I mentioned this last time too, is the non-linearity, photon-photon scattering. Don't try it because it has a trace of 16 gamma matrices in it, but write down the matrix element. All right, that'll, I think, have 8. But, write it out and just, ponder what it would take to actually compute it. But, be a little thrilled by the fact that, Maxwell's wrong. Photons scatter. So, we've got some really new stuff here. The Klein-Nishina formula, take a look at that, compare it to the Thomson scattering formula. If you just compute, classically, impact parameter and a photon passing an electron, and something like that, the Thomson scattering formula can be gotten as a certain limit of Klein-Nishina. But we're really getting some new results here. So it's worth learning all these techniques and really seeing how the quantum interference really leads to something that you just don't get otherwise. Okay, so good to see you all. See you all again next Monday, if not sooner. Don't hesitate to be in touch. Let me know how it's going. Work together, all of that.
I had a quick question actually.
Yeah, sure.
Yeah, sorry, I'm getting there. This is all new. This is cool. Does the actual form of the cross section affected by the form of normalization? Like, do these results get modified at all if we have a non-box normalization from the start?
Oh, the volume does not occur in the final formula. It's canceled out. So we can now take the volume to infinity.
Okay.
And in a practical sense, what counts as having asymptotically free states? Well, you've got that once you're a few meters away from the collision, you have asymptotically free states. If you have a box a light year across, the momentum states are so close, you might as well integrate them. So, take the limit or not, it doesn't matter. It doesn't affect the cross sections. Another thing that's often done is to take a ratio of cross sections. And if we were to do that, then my factor of 4 pi wouldn't matter either. Right. So if you've normalized things a little differently, but look at the ratio of cross sections for 2 different reactions, you can get some useful information that's independent of particulars of one or the other calculation or experiment. There are lots of ways of using these things. Another use, I think we'll talk about this when we talk about the strong interactions, hopefully not in the not too distant future. If you look at a total cross section for some decay, that depends on the number of possible decays. And what you see is as you go up in energy, all right, if we're looking at, say, let's look at an electron-positron annihilation, Baba scattering. Okay, one of the channels, the 2 particles annihilate, go into a photon, and and then pair produce again. Well, that can also happen if the energy is above 91 GeV. You could also produce a Z0 particle and do the same thing. So the cross section suddenly takes a step up at 91 GeV. So if you look at plots of the total cross section versus energy, you can see when a new particle enters the picture. You can use this as a test of the number of quarks. So up to the highest energies we can produce, there are 3 families of quarks. There are not 4, or you would see another step in the total cross section for certain particle production processes. There are very fascinating and subtle ways of getting information about the total picture from individual scattering experiments. So, well, yeah, go ahead.
Are those kind of 2 of the other, you just kind of mentioned that the box normalization scheme is like 1. Are there other normalization schemes where any of this changes? Or, yeah, I guess just fishing how much the box is relevant.
I think the box is a pretty standard approach to getting the differential cross section. I mean, it's fair, right? You're allowed to do that. We're not cheating here. It's not nearly as bad as renormalization. Okay, where you're going to absorb some infinities, or make sure some infinities cancel out. This. Well, a squared delta function looks like an infinity, but in a box, it really is not. So, this is a pretty tame technique. I don't think we really have to worry about that one.
As long as everything's like a complete space, if we don't have like a singularity hidden somewhere, then.
Oh yeah. Well, yeah. Now you're talking Hawking radiation or something, right?
Or yeah.
So
a punctured space or something. Yeah.
So have you read Hawking's original paper on Hawking radiation yet? You should.
A little bit.
Right. Yeah. It's not that bad. You have some initial quantum state. It's this kind of a scattering experiment, right? You've got some initial vacuum states, and they evolve, and you've got some final late time vacuum states. Only some of the states have fallen into the black hole. So there's a non-trivial unitary transformation from the initial to the final Hilbert space of states. It's called a Bogel-Yugoff transformation. It's just a unitary transformation of the A's and the A daggers into B's and B daggers. And it's non-trivial, which means that something that looks like a vacuum state initially is no longer a vacuum state at the end. Something that's annihilated by all the A's here is hit by some B daggers up there. And so it's a non-trivial state. It turns out it's a thermal state. And that's the black hole evaporation. And that's been looked at in a lot of different ways and holds up no matter how you decide to think about it, whether you think about local processes or you look at it in Rindler space. You can really get at these things and understand that the forces that actually lead to the particle production and things like that. It's actually a comprehensible paper. Go read it.
I think that the Unruh proof that I walked through, the Unruh proof with the Rindler space, is it basically just relies on it's like continuous but not connected or whatever, that there's the part that's accelerating away from you that you won't ever receive signals quick enough.
Yeah.
And
you
so,
lose some of the states. Some of the states have either crossed the Rindler horizon or fallen into the black hole. The picture is really pretty much the same.
And the math just looks like bound. It just looks like imaginary, or what are they called in E&M? The imaginary charges. They just look like they're boundary conditions of one another, both fields on either side. So they it's pretty straightforward. It's really not that bad.
Okay.
I think it depends. It depended on the connectedness. I think mostly it depended on there being if the space didn't have a boundary that was within it or something, like if it was at infinity, but
I'm not sure, Alex, because you can actually push the black hole singularity off to infinity, I think, at least for a Schwarzschild hole. So, I'm not sure that it's necessarily the topological character there that's doing it. It's the fact of an horizon. That's why you get it in Rindler space. There's no funny boundary in Rindler space. There's no funny topology going on there. It's just the fact of an event horizon, whether apparent or real physical event horizon. Everybody's looking tired and scowling. Go away. Unless you have questions, I'm happy to stay and answer questions. But yeah. All right. See you here. Well, all right. Bye.
Thanks, Professor. Sorry.
Oh, you bet. No, that's fine. Yeah, I was seeing a lot of sagging eyes there, but
yeah, because I'm being bad.
No, it's a good question. I don't think the Hawking radiation is down to topology. Well, no, I shouldn't say it that way, because that's just wrong. Right? It is topology. It's global topology, but it's the causal topology, not holes and multiple connectedness or anything like that. It's the topology of the causality.
See, because I thought that the Hawking radiation is universal because, in the Rindler acceleration, you'll accelerate and you'll see the vacuum heat up as you're going by it, just because you're accelerated. But you, if you measure the vacuum of that would be the unitary Boglobov transformation is the one where you're in flat spacetime just accelerating. And then you just redefine your vacuum. Your vacuum is different than the other person. But in the black hole, you get the topological defect where the left half of the Rindler wedge is 0. So you get a boundary. And I think that was where you get the Hawking radiation isn't just a Boglobov transformation, because half of it, it's half analytic. It's analytic on the right half of the wedge, but it's continued into the left, but the left continuation doesn't exist. Or that was the proof I saw, we just cut the wedge out. So it was a bit ad hoc, but
yeah, it's causally inaccessible, right? Yeah. And that's that's a kind of boundary, but it's a boundary because of the let's see, what is it? How would you say it? It's got to do with the time-like killing field.
Is on the surface.
It's how you define time, and in the presence of constant acceleration, in the case of the Rindler wedge, or in the case of a black hole, you define your time-like killing vector to be something that seems to be accelerating. From infinity, it looks like it's undergoing a uniform acceleration in either case, and that it actually is nonetheless a time-like killing field. But if you define your space of states relative to that time, you're defining a different space of states than if you just have some, asymptotically flat Minkowski space a long time ago.
Yes.
And it's the difference between those two spaces of states that really looks like radiation.
That's right, because in both of these, the proof that I saw we were doing, is it the ADM or whatever, we were comparing to asymptotic infinity in both of the, was our energy measure was from asymptotic infinity in both of the.
Yeah,
okay.
Right, yeah. And Hawking's first paper on this was definitely looking at these infinite past and future and just comparing the states there. Later, I think it may have been Hawking who talked about it, but people develop this local picture of pair creation near the horizon, and you know, some kind of local picture for how you might describe what's going on. And yeah, I was surprised to see how it worked, but it does in fact work. That the particle that falls into the black hole, seen from infinity, looks like it's got a negative mass, even though locally it's a perfectly normal, you know, particle of some sort. Its world line looks space-like from infinity, relative to you know, the coordinate system in infinity, and so it that has the effect of lowering the mass of the black hole because you've thrown a space-like particle into it.
That proof I saw a little bit in the I read Blanford-Schneik's article, and they did it a little bit, but I still haven't quite. Where did you see that art? Have you seen a good proof of the pairwise production? I'm still a little fuzzy.
I'm thinking maybe Hawking's second paper on the subject, and this would have been what, the 70s, right?
Oh, did he? He suggested it.
But you know, you also look at Wald and Unruh. You know, there are several people who did a lot of work on this back in the late 70s into the early 80s, probably. Yeah, I know that. Yeah, maybe it was Wald who looked in the Rindler wedge and asked, well, you know, if there's seeing radiation, where'd the energy come from? And they were able to build a simple model of, you know, a particle field relative to this accelerating frame, and to show that the energy is actually provided by the accelerating force. So, so you know, people have looked in that kind of detail at how this all works.
And I think the BZ, they kind of picked up halfway through that proof. And so what they said is it can be shown that in a rotating black hole, that pair production shell gets moved out into the ergosphere a little bit. They use some argument to perturb that out, and then that's what they used to describe some, like they were using it to do E&M in the seventh perturbatively next to a black hole. But okay, I'll look at Hawking's original, and I'll check out Wald, because they just like jumped into the proof halfway through, and then we're like, oh, and this is what it looks like in a rotating frame, by the way, with a magnetic field. And it's like, oh, okay, well, I get this, but
yeah, it often pays to go back to the original literature. You know, these questions were fairly hotly debated, not to pun too badly, but you know, people had to be convinced that black holes really radiated, and so people did a whole lot of work following Hawking's original paper on the subject, you know, exploring whether, you know, from this point of view or that point of view, this really happens, and it really does. You know, I think there's a wonderful paper on this by, might be Bekenstein. It might be called, it's something like Black Holes Really Do Radiate. Because, you know, after all this discussion had taken place, somebody says, you know, asks, do black holes really radiate? And made the argument that they don't. And Bekenstein, I think among many peers, was chosen to write an answer to that, and made a very nice, cogent argument. I hope I'm remembering that rightly. It could be that Maria or Charlie would remember that better than I am, but yeah, it's a lovely article, and I might have it right.
Okay,
but
I'll go fishing.
Yeah, okay, good luck.
No, this is perfect. Thank you, Professor.
Oh, you bet. Yeah, have fun with that. That's cool stuff.
I will.
All right.
Okay.
So
I think I got the fourth photon one, but I'll do my mass and then I'll send you both.
Oh yeah, good. Okay. Yeah, I haven't written that down yet, but you know what the diagram looks like. So
it's not that bad then.
Yeah, it shouldn't be hard to write the matrix element, just to square it.
It's just fun.
Yeah. Okay. I'll
Thanks,
see you.
Professor.
Take care.
Bye-bye.